Everything you know about the cosmos could be wrong. The opposite of a single fact is falsehood, but as physicist Niels Bohr realized, the opposite of one profound truth can be another profound truth. This video explores 25 cosmic paradoxes that tear at the fabric of our existence, from the nature of time to the very limits of what we can observe. These are not just intellectual riddles. They are profound mysteries that will force you to reconsider your place in the cosmos and the nature of your own consciousness. We will journey through ideas that defy common sense, revealing a universe far stranger and more wonderful than you ever imagined. By the end, your perception of reality will be fundamentally rewritten. We will confront why the universe is silent despite its vastness, and whether an object can be in two places at once just because you are not looking at it. Are you ready to question everything you think is real? The cosmos should be a roaring cacophony of alien chatter. With billions of stars in our galaxy alone, many older than our sun, the universe seems to offer countless opportunities for life to arise, evolve, and build civilizations. Statistically, the silence is deafening. This is the heart of the Fermi Paradox, a question posed by physicist Enrico Fermi during a casual lunch conversation in 1950. Looking at the vast potential for life, he asked a simple, devastating question. Where is everybody? The math seems to support his bewilderment. Frank Drake created an equation to estimate the number of detectable civilizations, and even with conservative guesses, the result suggests the galaxy should be buzzing with activity. We should see their ships, or hear their broadcasts, or stumble upon their ancient ruins. Yet our radio telescopes, like those in the SETI program, have listened for decades and heard nothing but the natural background hum of the cosmos. This profound silence leads to a disturbing possibility known as the Great Filter. This theory suggests that at some point from the origin of life to the development of a galaxy-spanning civilization, a barrier emerges. It could be that the initial spark of life is astronomically rare, or perhaps intelligence itself is a flawed evolutionary trait that always leads to self-destruction. Maybe the filter is ahead of us, a future catastrophe like environmental collapse, or a rogue artificial intelligence that every advanced culture eventually triggers. Other solutions are less grim but equally strange. Perhaps advanced civilizations are everywhere, but they have progressed to forms of communication we cannot begin to perceive, using neutrino messages or quantum entanglement in ways that are invisible to our primitive technology. Or they could be deliberately hiding, observing a galactic zoo where we are the isolated exhibit, not yet ready for contact. Are we truly the only ones in this immense dark ocean? Or is the universe teeming with life that is simply too alien, too advanced, or too cautious to say hello? This first paradox forces us to confront our own solitude and the fragile miracle of our existence. But this silence is only the beginning of the strangeness. That profound cosmic silence forces us to look inward, to a paradox that resides not in the distant stars, but within the very act of seeing itself. An electron fired at a screen does not behave like a tiny bullet. When no one is watching, it acts as a wave, passing through two slits at once and creating an interference pattern of possibilities on the other side. Yet the moment you set up a detector to see which slit it goes through, this ghostly wave behavior vanishes. The electron suddenly acts like a single particle, going through one slit or the other. It is as if the particle knows it is being watched and changes its behavior to suit our expectations. This is the double-slit experiment, and it demonstrates the core of the observer effect. The physicist Werner Heisenberg codified this weirdness with his uncertainty principle. He showed that at the quantum level, you cannot know everything about a particle at once. The more precisely you pin down its location, the less you can know about its momentum, and vice versa. This is not a limitation of our instruments. It is a fundamental property of reality. The universe, at its smallest scales, is not built on certainty but on a cloud of probabilities. This leads to the staggering idea of the wave function collapse. Before a measurement, a particle exists in a fuzzy superposition of all possible states, like a spinning coin in mid-air. It is both heads and tails, here and there, all at once. The act of observation, of measurement, forces this cloud of potential to collapse into a single, definite reality. The coin lands, showing one face. But what constitutes an observation? This question leads to one of the most famous thought experiments in all of science, devised by Erwin Schrödinger. He imagined a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and the cat dies. If not, the cat lives. According to quantum rules, the radioactive atom enters a superposition, meaning it has both decayed and not decayed. Therefore, the cat, linked to this quantum state, must be both alive and dead until someone opens the box and looks inside. This absurd scenario was meant to highlight the strangeness of applying quantum rules to the everyday world. Yet it forces a deep, philosophical question. Does the moon exist when you are not looking at it? Does reality have a definite state independent of any conscious observer? Or do we, through the very act of perception, force a single reality into existence? This paradox blurs the line between the observer and the observed, suggesting that our consciousness is not merely a passive receiver of the universe, but might be an active participant in its creation. If our glance can force a single electron to choose a path, what else might our minds be shaping without our knowing? This blurry line between observer and reality suggests that our very perception might shape the cosmos. But what if the flow of time itself is just as malleable? One twin embarks on a journey to a distant star at nearly the speed of light, while the other remains safely on Earth. Upon the traveler's return, a bizarre reunion occurs. The astronaut twin is still youthful, while the Earth-bound sibling has aged decades. This is the twin paradox, a thought experiment that rips apart our everyday experience of time. It is not science fiction, but a direct, stunning consequence of Einstein's theory of relativity. Time is not a universal metronome ticking at the same rate for everyone. Its passage is relative, warped by both velocity and gravity. For the twin racing through space, time literally slows down. This effect, called time dilation, means their heart beats slower, their thoughts process slower, and their entire biological clock runs in slow motion compared to the sibling back home. The equations that govern this, the Lorentz transformations, show that as an object approaches light speed, its experience of time compresses toward a standstill. But this creates an apparent contradiction. From the traveling twins' perspective, couldn't they argue that it was the Earth that moved away at high speed, making the Earth-bound twin the younger one? The resolution lies in acceleration. The journey is not symmetrical. The traveling twin is the one who feels the forceful thrust of the rocket to turn around and come back. This break in symmetry confirms that the astronaut is the one in motion, and thus the one who ages less. We have confirmed this with astonishing precision. In the Hayfel-Keating experiment, scientists flew atomic clocks on airplanes around the world. When these clocks landed, they were ever so slightly behind identical clocks that had remained on the ground. A more everyday application is the global positioning system. The satellites in the GPS network are moving at high speeds and are in a weaker gravitational field than Earth's surface. Their onboard clocks actually run faster because of these relativistic effects. If engineers did not constantly correct for this time warp, your phone's GPS would be wrong by several miles within just a few hours. So is time a river that flows at the same rate for all, or is it a personal journey, a path you carve through the cosmos with your own motion? This paradox forces us to see time not as a backdrop, but as a dynamic, flexible dimension of the universe, woven inseparably with the fabric of space. If time itself is this fluid, then what does that mean for the very arrow of time? The one-way street from past to future that we all take for granted. The fluidity of time opens a dizzying possibility, one that has captivated storytellers and physicists alike. What if you could swim against that river, journeying not just through time but backward into your own past? This thought leads directly to one of the most famous logical traps in all of science, the grandfather paradox. Imagine you build a time machine and travel back to a time before your parents were born. You find your grandfather and, whether by accident or design, prevent him from ever meeting your grandmother. This single act would erase the possibility of your own birth. But if you were never born, how could you have traveled back in time to commit the act in the first place? The paradox creates a perfect, maddening loop of cause and effect that seems to make backward time travel an impossibility. This is not just a plot device from science fiction. The equations of general relativity, crafted by Albert Einstein, do not explicitly forbid it. Certain solutions, like those involving rotating black holes or theoretical constructs called closed time-like curves, mathematically describe paths that loop back on themselves, allowing for travel into the past. Physicists like Kip Thorne have seriously explored whether traversable wormholes could function as time machines. If you could take one mouth of a wormhole and accelerate it to near light speed, and then bring it back, time dilation would mean that the accelerated mouth has experienced less time. Step through from the young side, and you would exit from the old side into its past. The physics allows for the concept, but the paradox remains a formidable barrier. So how could the universe resolve this logical inconsistency? One compelling idea is the Novikov self-consistency principle. Proposed by physicist Igor Novikov, this principle asserts that the past is already set in stone. If you travel to the past, you are not creating a new timeline. You are simply fulfilling a history that has always included your actions. You would find it physically impossible to kill your grandfather. Your gun would jam, you would miss the shot, or some other intervention would occur to ensure the past you remember remains intact. Your free will in the past is an illusion because you were always there as part of a single, consistent story. Another, even more mind-bending resolution comes from the many worlds interpretation of quantum mechanics. In this view, every possible outcome of every quantum event actually happens, but in a different, newly branching universe. Under this model, time travel would not send you into your own past, but into the past of a parallel reality. In that new timeline, you could indeed prevent that version of your grandfather from having children. You would not erase yourself. You would simply strand yourself in a universe where you were never born, leaving your original timeline completely untouched. This transforms the paradox from a logical loop into a one-way ticket to a different reality. We see these ideas play out in our stories. In Back to the Future, Marty McFly accidentally alters his parents' meeting, and he must race to restore the timeline before he and his siblings fade from a family photograph. The film brilliantly illustrates the chaotic ripple effects of changing the past. But does this mean our own past is a fragile thing, or is it an immutable fortress? The grandfather paradox forces us to confront the very bedrock of reality, causality itself. Is the chain of cause and effect an unbreakable law, or merely a suggestion that can be rewritten? This question of a fixed destiny versus a malleable history leads us to an even deeper mystery, one that suggests the entire universe might be a cosmic contingency, a single winning ticket in an infinite lottery of possibilities. That unsettling idea of a predetermined history opens the door to an even stranger loop, one where things do not just happen, but happen again and again without ever beginning. A time traveler, a devoted fan of Beethoven, journeys to 19th century Vienna hoping to hear the master's Fifth Symphony performed. To his dismay, he discovers Beethoven never composed it. Distraught, he pulls out his own copy of the sheet music and gives it to the young composer. Beethoven, inspired, publishes the symphony as his own, and it becomes the celebrated work we know today. The music exists, but who truly created it? This is the Bootstrap Paradox, a mystery of information or objects trapped in a causal loop with no discernible origin. They are not created, they are just there eternally. The name comes from the phrase pulling yourself up by your bootstraps, an impossible task that perfectly captures the absurd, self-creating nature of these loops. Unlike the grandfather paradox, which threatens to erase itself through logical contradiction, the Bootstrap Paradox is perfectly self-consistent. It presents no logical flaw, only a profound philosophical one. It challenges our most basic assumption that everything, every idea, must have a cause, a creator, a starting point. The universe, in this view, could be filled with these closed loops, where cause and effect are not a straight line but a circle, with no clear beginning or end. The scientific possibility for such loops comes from the same place as other time travel mysteries, from Kurt Gödel's solutions to Einstein's equations of general relativity. He found that in certain universes, closed time-like curves could exist, paths through space-time that loop back on themselves, allowing for a journey into your own past without ever leaving the timeline. This is the mathematical backbone for a causal loop. A more physical example is Polchinski's paradox, a thought experiment proposed by physicist Joseph Polchinski. He imagined a billiard ball shot into a wormhole, a hypothetical tunnel through space-time. The ball emerges from the other end of the wormhole in the past, at just the right angle to collide with its younger self, knocking it precisely into the wormhole in the first place. The ball's entire journey is a single, unbreakable loop. There is no initial cause for the ball entering the wormhole. It was simply always destined to happen that way. This forces us to ask a deeply unsettling question. Can something truly come from nothing? In a bootstrap loop, it appears so. The information for Beethoven's Fifth, the mass and velocity of the billiard ball, all of it is simply conserved within the loop, never created and never destroyed. This suggests that our relentless search for first causes, for ultimate origins, might be missing the point. Perhaps the universe does not require a beginning in the way we think. Perhaps reality is not a story with a clear start and finish, but an intricate, self-consistent tapestry of events where the concepts of beginning and end are themselves illusions. If a symphony can compose itself, what else about our world is just a stable, timeless pattern in the cosmic weave? If the universe can be a self-composing symphony, perhaps its entire score is written in a language we cannot see, a code running on a cosmic computer. The simulation paradox asks a question that seems ripped from science fiction, but is taken seriously by philosophers and tech visionaries alike. What if our reality, from the farthest quasar to the feeling of rain on your skin, is not the base level of existence, but an incredibly advanced simulation? Nick Bostrom formalized this mind-bending idea with a stark trilemma, a set of three possibilities, one of which must be true. First, almost all intelligent civilizations go extinct before they can reach a post-human stage capable of creating such simulations. Second, those that do reach that technological pinnacle have no interest in running ancestor simulations, perhaps for ethical reasons. Or third, and this is the startling one, we are almost certainly living in a simulation right now. The logic is simple. If even one advanced civilization ever chooses to run a vast number of detailed simulations, the number of simulated minds would utterly dwarf the number of original biological minds. Therefore, if you are a conscious being, the odds are overwhelmingly high that you are one of the simulated ones. Elon Musk has pointed out that the pace of our own technological progress makes this seem plausible. 40 years ago we had Pong, 2 rectangles and a dot. Now we have photorealistic, three-dimensional virtual worlds populated by millions of players. If that rate of advancement continues, creating a reality indistinguishable from our own seems not just possible, but inevitable. But if we are simulated, does that make our lives, our loves, and our struggles any less real? Philosopher David Chalmers argues no. He suggests that consciousness could be a fundamental property of the universe, something that emerges from the right organization of information, whether that information is processed by biological neurons or by lines of code in a supercomputer. A simulated mind that thinks, feels, and wonders about its own existence is, for all intents and purposes, a conscious mind. The technological requirements for such an ancestor simulation are beyond our grasp, but not necessarily beyond the laws of physics. Instead of simulating every single subatomic particle, which would be impossibly resource-intensive, an advanced simulator might use a rendering trick, similar to a video game. It would only generate the details of the world when someone is looking. Just like a game only renders the part of the world your character can see. This concept of optimized processing leads to a tantalizing question. Could we find glitches in the matrix? Some have speculated that the weird fuzziness of the quantum world, where particles exist as probabilities until observed, might be a sign of computational efficiency, a way to save processing power. The very constants of nature, the finely tuned numbers that allow our universe to exist, could be the initial parameters set by the programmer. The film The Matrix explored this concept dramatically, depicting a world where humans are unknowingly trapped in a simulated reality while their bodies are used as an energy source. While the science of using humans as batteries is flawed, the core philosophical question remains powerful. How can we trust our senses? If our reality is a simulation, then every memory we have, every law of physics we have discovered, could be part of the programmed backstory. So are we living in base reality, the original universe, or are we nested deep within a vast hierarchy of simulations, like a dream within a dream? This paradox does not just challenge what is real, it challenges the very authenticity of our own experience, suggesting that the solid ground beneath our feet might be nothing more than a perfectly rendered illusion. And if our reality is a construct, then what about the space it occupies? Is the vast, expanding cosmos we observe also part of the simulation, or could its immense scale be the ultimate glitch, a clue to a deeper truth hidden in plain sight? That perfectly rendered illusion of reality rests on a foundation of memory and a continuous past. But what if even that is a mirage? A single, conscious brain floats in the void, complete with fabricated memories of a childhood, a career, and loved ones, all spontaneously assembled from a random collision of particles. This is the Boltzmann Brain, a thought experiment so disturbing it threatens to unravel everything we think we know about our own existence. It emerges from the profound work of physicist Ludwig Boltzmann, who connected the concept of entropy, the measure of disorder in a system, to the arrow of time. The universe naturally progresses from order to disorder, which is why we remember the past and not the future. Yet Boltzmann's own statistical mechanics revealed a terrifying loophole. In a system that lasts for an eternity, even the most wildly improbable events must eventually happen by pure chance. Given enough time, a fully formed, conscious brain could simply pop into existence from the random jostling of atoms in the empty space around us. This brain would have memories of a structured life in an ordered universe, even though it just began an instant ago in total chaos. The paradox becomes brutally clear when we apply it to modern cosmology. In an infinitely old and vast universe, the number of these random, disembodied Boltzmann brains should vastly outnumber the number of ordered, biologically evolved beings like us. So why are we seemingly normal humans embedded in a 13.8 billion-year-old cosmos, and not lonely, momentary flashes of consciousness in the dark? Cosmologists like Sean Carroll grapple with this problem because it suggests our most basic assumption, that our past is real, might be catastrophically wrong. If a Boltzmann brain can have a perfect, detailed memory of a yesterday that never was, how can we trust that our own recollection of the Big Bang, of dinosaurs, or even of what we had for breakfast, is authentic? The universe, according to this logic, should be dominated by these phantom observers, not by us. This forces physicists to seek resolutions that prevent a cosmos overrun by illusory minds. One leading idea involves the inflationary multiverse. If our universe is just one bubble in an endless, expanding froth of universes, and most of these other bubbles have conditions utterly inhospitable to any life, then the overall probability of a Boltzmann brain forming is pushed down. In this vast landscape, a stable, long-lived universe like ours, which produces real, evolved observers, might not be so improbable after all. Another, more radical solution is the quantum death hypothesis, which suggests that any universe that has the potential to eventually produce Boltzmann brains is fundamentally unstable and will decay into nothingness long before that can happen. Our very existence, then, is proof that our universe is not of that unstable type. To grasp the personal horror of this paradox, picture waking up one moment with the unshakable conviction that you have lived a full life. You remember your first day of school, your wedding day, the faces of your children, but all of it is a phantom script, written by randomness an instant ago. You have no way to prove that your past is real. This is the ultimate epistemological nightmare, a crisis of knowledge that the Boltzmann brain creates. It does not just question the reality of the external world. It questions the very fabric of your inner self, your autobiography, your identity. If our consciousness can be a random accident, then what meaning can we assign to our history, our struggles, and our achievements? This paradox pushes us to the precipice, forcing us to wonder if we are part of a grand cosmic narrative or merely a fleeting, insignificant fluctuation in an endless sea of chaos. That profound uncertainty about our own memories echoes a deeper cosmic anxiety, a fear that the universe itself might be forgetful. Matter and energy can never be truly destroyed, only transformed, and this principle of conservation extends to information itself. Every particle, every interaction, carries a kind of cosmic data tag, a record of its properties and history. This information is, according to quantum mechanics, supposed to be permanent and indestructible. Yet, a black hole presents a terrifying exception. When anything crosses the event horizon, the point of no return, it seems to be erased from our universe forever. Its information is lost, creating a fundamental clash between Einstein's general relativity and quantum theory. This is the black hole information paradox, and it was Stephen Hawking who brought this conflict to a head. He realized that black holes are not completely black. Due to bizarre quantum effects at the very edge of the event horizon, they slowly leak radiation. This Hawking radiation is incredibly faint, but over eons, it causes the black hole to evaporate, shrinking until it potentially vanishes entirely. The problem is, Hawking's original calculations suggested this radiation was completely random, a thermal fuzz carrying no information about what fell in. If the black hole disappears, the information it swallowed disappears with it, violating a sacred rule of quantum physics. It would be like burning a book. The paper and ink are transformed into smoke and ash, and to our eyes, the story is lost forever. But quantum mechanics insists that in principle, if you could collect every single speck of ash and every wisp of smoke, you should be able to reconstruct every word. Hawking's claim was that for a black hole, even that ultimate reconstruction is impossible. The book is not just burned, its very existence is erased from the cosmic library. This idea horrified many physicists, leading to a famous bet between Hawking and Leonard Susskind. Susskind argued that information must be preserved, and he, along with others, developed a revolutionary idea to save it, the holographic principle. This principle suggests that all the information about everything that falls into a black hole is not lost inside its mysterious interior. Instead, it is encoded on the surface of the event horizon, like a cosmic DVD. A three-dimensional object is translated into a two-dimensional pattern on the boundary. When Hawking radiation escapes, it is not random, it carries this encoded information away, pixel by pixel, as the black hole evaporates. This resolves the paradox, but at a staggering cost. It implies that our perception of a three-dimensional world might be a projection, a holographic illusion arising from a two-dimensional reality at the universe's edge. This elegant solution, however, created another puzzle, the firewall paradox. If information is being scrambled and radiated from the event horizon, does that mean the horizon is not the smooth, empty space Einstein predicted, but a searing wall of high-energy particles that would incinerate anything falling in? The debate rages on. Is information preserved, duplicated, or lost? The answer cuts to the heart of whether the universe is fundamentally predictable and orderly. If information can be truly lost, then the cosmos has a permanent memory leak, and the chain of cause and effect can be broken. But if the holographic principle is correct, then reality is far stranger and more interconnected than we ever dreamed. A vast cosmic projection where the deepest truths are written on the surface of the void. And if information is the fundamental substance of reality, then what happens when we try to copy it, to know it completely? Does the universe itself impose a limit on what we can truly know? This bizarre preservation of information on a black hole's surface hints at a universe where observation is deeply woven into the fabric of events. But what if watching something could do more than just record it? What if watching could literally freeze it in place? An unstable radioactive atom is poised to decay, a quantum ticking clock. Left to its own devices, it will eventually transform. But if you measure it, checking its state again and again in rapid succession, a strange thing happens. The atom never decays. Your constant gaze has locked it into its initial state, as if you have stopped time for that single particle. This is the quantum Zeno effect, a phenomenon where continuous observation prevents change from occurring. Its name is a tribute to the ancient Greek philosopher Zeno, who crafted paradoxes arguing that motion itself is an illusion. In his most famous puzzle, an arrow in flight must, at any single instant, be motionless in a specific place. How then, Zeno asked, can a sequence of frozen instants ever add up to movement? The quantum Zeno effect brings this philosophical riddle into the laboratory, showing that at the quantum level, watching something intently can indeed make it stand still. The mechanism lies in the heart of quantum mechanics. A particle's state is described by a wave function, a cloud of probability that evolves smoothly over time according to the Schrödinger equation. When you measure the particle, you force this wave function to collapse into a definite state, a process called the projection postulate. Now imagine you measure the particle almost immediately after that first observation. Its wave function has barely had any time to evolve and spread out into other possible states, like decay. Your repeated measurement collapses it right back to its starting point. If the measurements are frequent enough, the system is perpetually reset, trapped in its initial condition like a scratched record that keeps jumping back to the beginning. This is not just a theoretical curiosity. It has been demonstrated in stunning experiments with trapped atoms and ions. Scientists can use laser pulses to repeatedly measure whether an atom is in a particular energy state. When they do this rapidly, they can effectively prevent the atom from transitioning to a higher energy level, freezing its quantum evolution. This active control through observation has profound implications for the future of technology, particularly in quantum computing. Quantum computers rely on qubits, which exist in fragile superpositions of 1 and 0. The great enemy of a quantum computer is decoherence, where the qubit's delicate state collapses from random environmental interference. The quantum Zeno effect offers a potential defense. By strategically measuring the qubits, we might be able to protect them from decoherence, actively stabilizing the quantum information and preventing errors from creeping in. It is a form of quantum babysitting where a watchful eye keeps the system in line. This leads to a deeply philosophical question, a quantum twist on the old saying that a watched pot never boils. Does intense focus actually alter the physical world? Can we control outcomes merely by paying attention? The quantum Zeno effect suggests that observation is not a passive window into reality, but an active force that intervenes in the processes it seeks to understand. It reinforces the strange intimacy between the observer and the observed, a relationship where consciousness, through the physical act of measurement, becomes a participant in the dance of reality. How much of the stable world we experience is a product of a constant, low-level observation from the environment around us? This paradox pushes us to see our attention not just as a mental state, but as a tangible influence on the quantum stage, a subtle power to hold the world in place, if only we look closely enough and often enough. But if our gaze can halt change, what other unseen forces might be sculpting the cosmos from the shadows, perhaps hidden in the very emptiness of space itself? The darkness of the night sky is a profound cosmic clue. If the universe were truly infinite, eternal, and static, then every single direction you looked would eventually land on the surface of a star. The entire celestial sphere should be a solid, blinding sheet of light, as brilliant as our sun. This glaring contradiction is Olbers Paradox, named for the German astronomer Heinrich Olbers, though the puzzle had troubled thinkers for centuries. Why, in a cosmos that seems so vast, is the night sky so profoundly dark? The answer unravels the very story of our universe. One early, poetic insight came from an unlikely source, the writer Edgar Allan Poe. He mused that the darkness of space was a glimpse into a finite past, suggesting the universe had not existed forever. So the light from the most distant stars simply had not had time to reach us. He was right. The universe is not infinitely old, it has a birthday. The Big Bang occurred roughly 13.8 billion years ago, which means we live within a cosmic horizon, a sphere of space from which light has had time to travel to our eyes. We cannot see beyond this horizon, and so an infinite number of stars do not fill our view. The expansion of the universe provides the second, crucial piece of the puzzle. Space itself is stretching, and this stretches the light traveling through it, shifting it to longer, redder wavelengths. For the most distant galaxies, this redshift is so extreme that their visible starlight is stretched into the invisible infrared, effectively draining their energy and fading them from view. This is why the sky is not flooded with the combined light of all eternity. Some might think that cosmic dust blocks the light, but this is a temporary fix. Over immense spans of time, that dust would absorb so much starlight that it would heat up until it glowed just as brightly as the stars themselves. Think of it like standing in an infinite forest. At first, the nearby trees block your view. But if the forest goes on forever, every line of sight would eventually find a gap between the trunks, revealing a tree in the distance. The forest's canopy would appear solid. Our night sky is dark because the cosmic forest is not infinite, and it is actively growing, pushing the most distant trees into a darkness we cannot see. This paradox led directly to one of the greatest discoveries in human history. That remnant glow from the universe's fiery birth, the cosmic microwave background, is the ultimate proof. It is the cooled-down, redshifted afterglow of the Big Bang, a uniform whisper of heat that fills all of space. It is the final, faded testament to a time when the entire sky truly was as bright as the surface of a star. So the simple act of looking up at a starry, black sky is not just an observation of beauty. It is direct evidence that our cosmos had a beginning, that it is dynamic and evolving, and that it is not an eternal, static arena. The darkness between the stars is not empty nothingness. It is the signature of a finite story, a cosmic timeline with a definitive start. If the darkness tells us the universe had a beginning, what other secrets are written in the faint, ancient light that fills the void? That subtle power of observation to freeze a quantum state hints at a stability that might be an illusion because in the grander scheme, nothing truly stands still. An ancient Greek legend tells of the Ship of Theseus, a revered vessel preserved in the Athens harbor. Over the decades, as its wooden planks rotted, each one was carefully replaced. Eventually, not a single original piece of the ship remained. The philosophers then asked a devastatingly simple question: is this reconstructed vessel still the Ship of Theseus? If not, at what point did it cease to be the same ship? This 2,000-year-old thought experiment is not just a philosophical game. It strikes at the very heart of identity in a cosmos defined by relentless change. Every object you consider permanent is in a state of constant flux. The stars in the night sky are not the same from one moment to the next. They are colossal furnaces fusing hydrogen into helium, expelling their own mass in stellar winds, and will one day die, scattering their enriched guts across the galaxy to be recycled into new stars and planets. Our own sun sheds millions of tons of material every second. The Andromeda Galaxy is on a collision course with our Milky Way, a slow-motion dance that will fundamentally reshape both structures. On a more intimate scale, your own body is a living testament to this paradox. Nearly every cell in your body is replaced over a span of about 7 years. The atoms that comprised you a decade ago are mostly gone, scattered back into the environment. Are you, then, the same person you were as a child? Your memories and your sense of a continuous self scream yes, but your physical substance tells a different story. Thomas Hobbes added a devilish twist to the original paradox. He wondered what would happen if all the old, discarded planks from the Ship of Theseus were collected and meticulously reassembled into a second ship. Which one now holds the true identity, the continuously maintained ship or the reassembled relic? There is no single easy answer, and that is the point. Physics deepens this mystery. At the most fundamental level, you are not a solid collection of atoms but a swirling cloud of quantum fields, temporary excitations in an invisible energy landscape. The particles that make up your hand are constantly being exchanged, interacting and flickering in and out of existence. There is no static you, only a pattern, a stable vibration that persists through the churning chaos. This is where the concept of four-dimensional objects in spacetime offers a radical perspective. In the block universe of relativity, an object is not just its three-dimensional shape at one instant. It is a long, worm-like entity stretching through time, from its beginning to its end. Your childhood self, your present self, and your elderly self are all different temporal cross-sections of the same four-dimensional being. Your identity is not a point, it is a timeline. The Ship of Theseus, in this view, is the entire history of its changes, not any single snapshot. So what is the thread of continuity? Is it the physical material, the specific planks and atoms, that seems unlikely as they are always being swapped out? Is it the structure, the specific arrangement of parts? But that structure also evolves. For us, the answer seems to lie in the intangible, in the pattern of information, the connected chain of memory and experience, and the continuous causal process that links one moment to the next. The universe does not seem to care about the identity of individual particles, only about the conservation of the overall patterns they form. This paradox forces us to abandon the idea of a fixed, unchanging essence. Nothing is permanent, and yet everything persists. A river is always new water, yet we give it the same name. A flame is a constant process of combustion, a rapid exchange of fuel, yet we see a single, dancing fire. We are all like that flame, a process, not a thing. A temporary pattern of energy and information, dancing for a brief moment in the cosmic dark, convinced of our own solidity. If even our own bodies are fleeting constellations of atoms, then what does that say about the fundamental nature of the reality we inhabit? This erosion of the self leads to an even more unsettling question, one that asks whether the universe we perceive is merely a shadow of a far richer, hidden reality. Our fleeting sense of identity confronts a universe where even the rules of evidence can be a hall of mirrors. To prove the statement that all ravens are black, you might think you need to find black ravens. Yet, formal logic presents a strange shortcut. The statement all ravens are black is logically equivalent to saying all non-black things are non-ravens. This means that observing a red apple, which is non-black and also a non-raven, technically and logically supports the original claim. This is the paradox of the ravens, formulated by philosopher Karl Hempel, and it reveals a deep crack in our intuitive understanding of scientific proof. Finding a single green sock in your drawer should not, in any practical sense, make you more confident that every raven on Earth is black. Yet the cold equations of logic suggest it does. This paradox strikes at the heart of inductive reasoning, the very process by which we build scientific knowledge from specific observations to general laws. In cosmology, this has profound implications. Our theories about black holes, for instance, might be indirectly confirmed not just by observing them directly, but by the conspicuous absence of their theoretical opposites. If our models predict that white holes which spew matter out cannot exist in a stable form, then our failure to ever detect one becomes a piece of evidence, a cosmic non-black non-raven that strengthens our understanding of the dark entities we do see. This is where the philosophy of science offers a crucial correction. Karl Popper argued that scientific progress is not made through confirmation, but through falsification. A theory can never be proven true, only proven false. We advance by relentlessly trying to disprove our best ideas. Searching for a single white raven is a far more powerful scientific act than cataloging a million black ones, because that one white raven would shatter the hypothesis completely. Consider the search for extraterrestrial life. Not finding life on Mars does not prove life is nowhere else in the universe. But according to a Bayesian view of probability, which updates the likelihood of a belief based on new evidence, each unsuccessful search of a potentially habitable world slightly lowers our overall estimation that life is common. We are constantly observing non-life on non-Earths, and each observation, like the red apple, ever so slightly adjusts our cosmic probabilities. So how do we know what we know? The paradox of the ravens forces us to confront the subtle traps in our quest for truth. It reminds us that not all evidence is created equal. 1,000 red apples will never carry the same weight as a single purple raven. In our journey to understand the cosmos, we must be critics of our own observations, constantly asking whether we are seeing the universe as it is, or merely finding comforting, logical excuses for our own assumptions. This careful dance between proof and disproof leads us to an even more fundamental question, one that challenges the very nature of the objects we study. What if the particles we believe to be the bedrock of reality are not really particles at all, but merely the ghostly vibrations of invisible, infinitely long strings? This same challenge of drawing a line in the sand appears in the very language we use to define the cosmos. A heap of sand sits on a table. If you take away a single grain, it remains a heap. Remove another, and it still seems like one. But if you continue this process one grain at a time, you are eventually left with a single grain on an empty table. At what precise moment did the heap cease to exist? This is the Sorites Paradox, a 2,000-year-old puzzle from the philosopher Eubulides of Miletus that attacks our instinct to categorize a continuous world with sharp, discrete labels. The problem is not with the sand, but with the vague and fuzzy nature of the word heap itself. This linguistic uncertainty ripples outward, all the way to our maps of the heavens. We saw this play out dramatically in our own solar system with the debate over Pluto. For decades, it was the 9th planet. But as we discovered more and more objects in the distant Kuiper belt, some nearly as large as Pluto, astronomers were forced to ask, what exactly is a planet? Is it just about size, or does its gravitational dominance in its orbital neighborhood matter? The International Astronomical Union chose the latter definition, and suddenly, Pluto was demoted to a dwarf planet. The boundary was drawn, but the underlying reality of that icy world did not change one bit. We face similar fuzzy boundaries everywhere we look in space. Take the line between a gas giant like Jupiter and a failed star known as a brown dwarf. Both are massive balls of gas, but a brown dwarf is just heavy enough to briefly fuse a rare isotope of hydrogen in its core, while a gas giant is not. Is this single nuclear reaction the ultimate dividing line between a planet and a star? Or is the universe presenting us with a seamless spectrum of objects, from small rocky worlds to giant planets to dim stellar embers, and our categories are just clumsy attempts to impose order? This paradox even touches our most fundamental assumptions about the cosmos. The cosmological principle states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every point. Yet when we look around, we see wild variations, from the terrifying emptiness of a cosmic void to the dazzling density of a galactic supercluster. We are asserting that the universe is smooth by averaging over its profound lumpiness. Where exactly does the small, lumpy scale end and the large, smooth scale begin? There is no clear answer. The world itself seems to resist our boxes. There is no single moment when day becomes night, only a gradual, beautiful dimming we call twilight. Modern mathematics has developed tools like fuzzy logic to handle these gradations, where something can be partially true and partially false at the same time, a far cry from the rigid true or false of classical logic. And at the most fundamental level, physics tells us that reality is inherently fuzzy. Heisenberg's uncertainty principle declares that a particle does not have a precise position and a precise momentum at the same time. The very fabric of spacetime, according to general relativity, can be warped and curved, making a definitive, universal now impossible to define. So are the categories we use, from planet to star to universe, real features of the cosmos, or are they merely convenient fictions? Stories we tell ourselves to navigate an infinitely complex and continuous reality. This paradox suggests that the sharp edges we see in the world are often illusions of our own making, and that true understanding lies not in building better boxes, but in learning to appreciate the subtle, flowing gradients of existence. If our definitions are so fragile, how can we ever be certain we are measuring the universe itself, and not just the shadow of our own minds? We weep for characters who were never born, and we feel our hearts race at the sight of a doomed starship on a screen. This is the paradox of fiction, the strange truth that we have powerful, genuine emotional responses to things we know are not real. Why does the death of a fictional hero leave a real ache in our chest? Philosopher Colin Radford argued this is fundamentally irrational. How can we feel sorrow for a tragedy that never happened, for a person who never drew breath? Yet the tears we shed are undeniably real, a testament to a deep and puzzling split within our own minds. Neuroscience offers a clue. Our brains are not cold logic machines, they are magnificent simulators. When we become immersed in a story, the same neural networks that light up during real-life experiences are activated. The fear you feel watching a monster creep through a spaceship corridor is a ghost, a simulated echo of a real threat, but your body reacts as if it were true. Your pulse quickens, your muscles tense, all triggered by pure imagination. This blurring of lines between the simulated and the real is not confined to the movie theater. It lies at the very heart of how we explore the cosmos. Scientists can develop fierce, almost personal attachments to their theories. They will fight for the elegance of string theory or the multiverse with a passion that goes far beyond cold calculation. These are, for now, just mathematical landscapes, unproven hypotheses. Yet researchers invest years of their lives, their identities, their hopes into these conceptual frameworks. They are fighting for the life of an idea as if it were a living thing. This emotional investment is the engine of scientific discovery. It is the driving force behind the late-night calculations, the heated debates at conferences, and the relentless pursuit of a beautiful, elegant truth. Our communication of science leans on this same power. The story of the Big Bang is not just a list of equations, it is a cosmic genesis narrative. We speak of black holes as cosmic monsters, lurking in the void and devouring stars. We describe the eventual death of our sun, swelling into a red giant that will engulf the inner planets, and we feel a genuine pang of cosmic awe and melancholy for a future Earth that will not exist for billions of years. We are captivated by the hypothetical search for alien life, feeling a thrill of possibility and a shiver of fear at the unknown, all triggered by radio silence and mathematical probabilities. Why do these abstract concepts, these hypothetical cosmos, move us so deeply? They tap into the same neural machinery that makes us human, that allows us to care, to hope, and to fear. This paradox reveals that our journey to understand the universe is not a purely rational expedition. It is a story we are telling ourselves, a grand narrative where our emotional and rational minds are inextricably intertwined, working together to paint a picture of reality on the largest possible canvas. If our feelings for fiction are real, then perhaps the stories we tell about the cosmos are more than just theories. They are the very language through which we connect with the profound mysteries of existence. That same profound uncertainty about our own definitions confronts us in the very act of moving through the world. To cross the room, you must first reach the halfway point. But before you can get to that midpoint, you must reach the quarter point. And before the quarter point, the eighth point, and so on forever. This is Zeno's Dichotomy Paradox, a 2,000-year-old argument that suggests any journey is composed of an infinite number of steps, making motion itself a logical impossibility. You are forever approaching your destination but never truly arriving, trapped in an endless subdivision of space and time. This ancient Greek puzzle is more than a clever riddle. It strikes at the heart of whether the universe is a smooth, continuous fabric or a collection of discrete, indivisible chunks. For centuries, the mathematical solution seemed to lie with calculus. The genius of Newton and Leibniz was to show that an infinite series can have a finite sum. The sequence of 1/2 plus 1/4 plus 1/8 and so on adds up to exactly 1. Mathematically, you can indeed cross the room by completing an infinite number of steps in a finite amount of time. The limit converges and you arrive. But mathematics is a description of reality, not reality itself. Does the physical universe truly contain an infinite number of points between here and there? Modern physics suggests a startling answer: no. There appears to be a fundamental limit to how small things can get. This is the Planck length, a distance so minuscule that it is to a meter what a single atom is to the entire observable universe. At scales this small, the very concepts of space and distance break down. The smooth geometry described by Einstein's general relativity is replaced by a roiling, chaotic foam, a quantum uncertainty in the fabric of spacetime itself. In theories of quantum gravity, like loop quantum gravity, space is not continuous. It is woven from a fabric of finite, indivisible threads. Area and volume come in tiny, discrete packets, a pixelation of reality at its most fundamental level. This provides a profound physical resolution to Zeno's ancient paradox. You are not taking an infinite number of steps. There is a final, smallest possible step you can take, a quantum of distance. Once you reach that scale, you cannot subdivide further. You either move that one quantum or you do not. The infinite regress is cut off by the granular nature of spacetime itself. This changes everything about our picture of the cosmos. Consider the Big Bang singularity, the point of infinite density from which our universe is thought to have emerged. If spacetime is discrete, then there is no true mathematical singularity, no point of infinite anything. There is only a state of maximum possible compression, a single, ultra-dense pixel of reality from which everything expanded. The smooth expansion of the universe, then, might be an illusion, much like the smooth motion of a movie is an illusion created by 24 static frames per second. The cosmos could be updating itself in tiny, discrete ticks of a cosmic clock. Imagine zooming into a fractal pattern on a computer screen. No matter how far you zoom, more intricate details keep appearing, an infinite descent into complexity. But your screen has a base resolution, a final pixel beyond which no more detail exists. Is our universe like that infinite fractal, or is it like the screen, with a fundamental resolution limit? The possibility of a pixelated reality challenges our most basic sensory experiences. The graceful arc of a thrown ball, the unbroken flow of a river, the seamless sweep of time, all of it might be an emergent illusion, a statistical average of countless tiny, quantum jumps. So is the universe continuous or discrete? Is motion a smooth glide or a rapid-fire sequence of quantum snapshots? Zeno's paradox, born from pure thought, now finds its answer not in philosophy, but in the deepest laws of physics, hinting that the stage upon which reality plays out may be grainy at its core. And if space itself is quantized, what other fundamental aspects of our existence might be built from these tiny, indivisible building blocks? A prisoner is sentenced to be hanged, but with a cruel twist. The execution, the judge declares, will take place at noon on some weekday next week, and it will be a complete surprise. The prisoner, a clever logician, reasons himself into a state of relief. It cannot be Friday, he thinks, because if I am alive on Thursday evening, I will know with certainty the hanging is the next day, and it would not be a surprise. Therefore, Friday is eliminated. But then, he continues, it cannot be Thursday either. With Friday removed, if I reach Wednesday evening unhanged, I will know it must be Thursday, and again, no surprise. He repeats this logic, eliminating each day in turn, until he concludes the hanging cannot happen at all. Confident, he rests easy. Yet on Wednesday, the executioner arrives at his cell, and the prisoner is genuinely, utterly shocked. The surprise was real. This is the unexpected hanging paradox, a dizzying loop of logic and knowledge that collapses under the weight of its own assumptions. The problem lies in self-reference. The prisoner's prediction about his own state of knowledge becomes part of the system, creating a contradiction that seems to make the surprise impossible, until reality steps in to prove it is not. In the grand theater of the cosmos, we face a similar puzzle. We try to forecast cosmic events, from the explosion of a distant supernova to the ultimate fate of the universe itself. But can a system that contains conscious observers truly predict its own future? The philosopher Michael Scriven argued that some truths are simply unknowable until the moment they happen. You cannot know the outcome of a future event with certainty until time itself delivers the answer. This has a startling parallel in quantum cosmology, where the act of observation is not a passive reading of the universe, but might be an active participant in its unfolding. The equations that describe the early universe are a haze of probabilities, much like the prisoner's week of possible hanging days. Does the act of a conscious observer measuring the cosmos today somehow force one of those ancient possibilities into a concrete reality, influencing the very history we are trying to decipher? This predictive loop appears in the chilling doomsday argument, a probabilistic reasoning that uses the total number of humans born so far to estimate our species' future lifespan. The argument suggests that we are likely somewhere in the middle of the total human population, meaning if humanity were to flourish for millions of years, the odds of you being born in the first few 100,000 years are vanishingly small. Therefore, it is more statistically likely that the end is much nearer than we hope. This is not a prophecy of doom, but another logical mirror, where our mere position in time is used to predict an end that, once predicted, could alter our behavior and potentially change the outcome. Consider a team of astronomers predicting a gamma ray burst from a dying star. Their anticipation does not cause the star to explode. The event is dictated by immutable laws of physics. Yet, our understanding of that event, the meaning we assign to it, and the scientific theories we build upon it are forever shaped by the prediction. We are not just observing the cosmos, we are in a conversation with it, and our questions might be subtly changing the answers we receive. So, can we ever truly know the future? Or does the very act of looking ahead cast a shadow that changes the path? This paradox reveals that knowledge is not a static snapshot of a predetermined world. It is a dynamic, often paradoxical, dance between the knower and the known, a dance where the steps are not fixed until the music finally plays. If our gaze can shape the quantum present, could our predictions also bend the arc of cosmic destiny? A simple question about a village barber can unravel the very foundations of logic. Bertrand Russell posed a deceptively simple riddle. In a certain town, a barber shaves every man who does not shave himself, and only those men. So, who shaves the barber? If he shaves himself, then by the rule, he must not shave himself. But if he does not shave himself, then he falls into the category of men who do not shave themselves, and the barber must shave him. This is the Barber Paradox, a perfect logical loop that exposes a fatal flaw in any system that allows for self-reference, where a definition or a set can try to include itself. This is not just a clever puzzle. It reveals that our most trusted tools for describing reality, logic, and mathematics have cracks in their foundation. This problem of self-reference echoes all the way to the heavens, forcing us to question the ultimate system, the cosmos itself. The mathematician Kurt Gödel delivered the formal blow with his incompleteness theorems. He proved that in any sufficiently complex mathematical system, there will always be true statements that cannot be proven within the system itself. The system cannot demonstrate its own consistency. It is like a rulebook that cannot confirm whether it is free of contradictions without looking at a higher rulebook, which itself would face the same problem. When we try to define the universe as everything that exists, we immediately run into a Russell-like paradox. If the universe is truly all that is, then what contains the multiverse? Is it part of everything, or is it outside our definition? Our language and logic strain at the seams when we try to box in ultimate reality. This self-referential loop appears in the anthropic principle, the observation that the universe's physical constants seem perfectly fine-tuned to allow for our existence. We are here to observe the universe precisely because its laws permit life. But this feels like a circular argument. It is as if the universe is fine-tuned because we are in it to see that it is fine-tuned. This is not an explanation for why the tuning exists, but a statement about the necessary conditions for our own observation. We are both the question and a prerequisite for the answer. A simpler version of this logical knot is the liar paradox. If a person says this statement is false, is it true or false? If it is true, then it must be false. If it is false, then it is true. This dizzying recursion mirrors what can happen in our grand cosmological theories. A theory of everything that attempts to explain all physical laws might, by its own rules, predict its own incompleteness or the existence of realities it cannot describe. So, are the laws of the universe truly self-consistent? Or do they contain unresolvable loops that we, from our limited vantage point, simply cannot see? The Barber Paradox is a humble reminder that our minds and our mathematics are part of the system they are trying to understand. We are not gods looking down on a cosmic machine. We are cogs within it, trying to reverse engineer the blueprint using tools that may have inherent, unprovable limits. If the very logic we use to define reality has boundaries, what does that say about the nature of the reality we are defining? Even our cosmic ambitions are haunted by the ghost of unintended consequences. An entire society, fearing an uncertain future, decides to save every spare dollar. This seems wise for each individual, a prudent step towards security. But when everyone does it at once, a strange reversal occurs. Spending plummets, businesses fail, unemployment soars, and the collective pool of wealth shrinks. The very act of trying to save more leads to a society that can save less. This is the paradox of thrift, an idea from economist John Maynard Keynes that reveals a painful truth. What is rational for the one can be ruinous for the many. And this principle of counterproductive self-interest might be written into the fundamental laws of the cosmos. The universe itself operates under a kind of cosmic economics, governed by the unbreakable ledger of energy conservation and the relentless trend of entropy. Energy cannot be created or destroyed, only transformed, and in every transformation, the overall disorder, the entropy of the universe always increases. This is the second law of thermodynamics in action. Life is the ultimate local saver, a stunning feat of cosmic thrift. A living organism is a pocket of exquisite order, a temporary rebellion against the universal slide into chaos. A single cell, a human brain, a civilization, all represent a dramatic local decrease in entropy. But this local gain comes at a global cost. To build and maintain this order, life consumes energy and expels waste, and in doing so, it increases the total disorder of the surrounding universe far more than the order it creates. Your very existence is a process that speeds up the universe's journey toward its final state. This end is known as the heat death, a future of maximum entropy where all energy is evenly distributed, temperatures equalize, and the cosmos becomes a static, featureless graveyard. No more stars will shine, no more processes can run. It is the ultimate economic collapse, a state of perfect, sterile equilibrium. The physicist Ludwig Boltzmann helped us understand this statistical drive toward disorder, showing that the arrow of time points irrevocably toward this diffuse and silent end. But how do we get from the vibrant, structured universe we see today to that bleak, uniform finale? The answer lies in the cosmic version of thrift. Consider a stellar nursery, a vast cloud of gas and dust collapsing to form new stars. Each new star is a triumph of local organization, a fusion engine that will shine for millions or billions of years. But from the perspective of the galaxy, each star's birth is an act of consumption. It locks away a huge reservoir of hydrogen fuel, burning it in one concentrated location instead of allowing it to be part of a larger, perhaps more complex galactic process. The very act of creating a local structure like a star uses up resources that could have contributed to the growth of other structures, potentially limiting the overall complexity and longevity of the galactic system. It is a trade-off, a sacrifice of potential global futures for a concrete local present. Do these local optimizations, these brilliant flashes of cosmic ingenuity, inevitably accelerate the global decay? Is the universe's magnificent tapestry of galaxies, stars, and planets merely the fleeting, beautiful side effect of a system spending its limited resources on its way to an irreversible bankruptcy? This paradox forces us to see the cosmos not as a collection of isolated events, but as a single, interconnected economy where every birth of a star and every spark of life is both a creation and a consumption, a step toward both local complexity and global simplicity. If the universe is spending its energy to create us, what does that say about the ultimate value of our temporary, ordered existence within the endless, expanding dark? Our economic choices reflect a strange cosmic bias. Water is the substance of life itself, yet we pay almost nothing for it. A diamond is a beautiful but functionally useless crystal, and we assign it immense worth. This is the classic paradox of value, and its implications reach far beyond our planet. The universe is filled with phenomena whose value we assign not by any intrinsic cosmic measure, but by our own human perceptions of rarity and utility. Think of the countless exoplanets we have discovered, rocky worlds orbiting distant stars. Many could be teeming with water and the basic chemistry for life, yet they are often seen as commonplace, less thrilling than the discovery of a single, rare, intermediate-mass black hole. The economist Adam Smith identified this puzzle, and the solution lies in the concept of marginal utility. The value of something is not determined by its total usefulness, but by the usefulness of one additional unit. The very last cup of water available to you is priceless, while the first 1,000 gallons are cheap. In a desert, you would trade a fortune in diamonds for a single canteen. This same logic shapes our exploration of the cosmos. We pour resources into studying the most violent, explosive, and rare cosmic events, like gamma-ray bursts, while often overlooking the profound, stable miracle of our own solar system. The Moon, for instance, is a scientific treasure trove. Its face is a preserved record of the early solar system. Its gravity stabilizes our planetary tilt, and its presence may have been essential for life to begin on Earth. Yet, because it is always there, a constant companion in our sky, we take it for granted. Its value is masked by its abundance in our lives. This leads us directly to the anthropic principle, the observation that the universe's fundamental constants appear perfectly fine-tuned to allow for our existence. We see this fine-tuning as incredibly valuable, a cosmic jackpot. But is it truly valuable, or is it simply a matter of chance? We are here to observe the universe precisely because these constants allow for life. In a multiverse of infinite possibilities, our universe is not special. It is just the one that worked for us. Its apparent value is, like the price of a diamond, a product of our own perspective. This reframes the Fermi Paradox. Is the silence of the cosmos a sign that life is so common it holds little value, making no effort to announce itself? Or is life so breathtakingly rare and precious that it must remain hidden to survive? Our answer depends entirely on the value we assign to consciousness itself. So what gives cosmic phenomena their true significance? Is it their rarity, their utility, or simply our awareness of them? This paradox forces us to confront our own cosmic priorities. We chase the brilliant, distant diamonds of the universe while standing knee-deep in the life-giving water of our own celestial backyard, often forgetting that the most profound marvels are the ones we have always known. Chasing happiness is a sure way to watch it vanish. This is the paradox of hedonism, a psychological trap where the direct pursuit of pleasure ensures its escape. The more desperately you grasp for joy, the more it slips through your fingers, only to find you when you are fully immersed in a meaningful task, a deep connection, or a state of pure wonder. This principle extends far beyond our personal lives, reaching into our very quest to understand the cosmos. Our frantic search for ultimate answers, for a single equation that explains everything, can blind us to the profound beauty of the mystery itself. The philosopher John Stuart Mill realized that happiness is not an end to be pursued, but a side effect of pursuing other ends, of engaging with life passionately. Viktor Frankl, drawing from his experiences in concentration camps, argued that the primary drive in life is not pleasure, but the search for meaning. We do not find purpose by seeking a comfortable state, but by having a reason to endure discomfort. This same dynamic fuels the engine of scientific discovery. The history of astronomy is filled with moments of brilliant serendipity, where the greatest revelations came not from a targeted hunt, but from scientists simply observing the universe with open curiosity. The discovery of the cosmic microwave background radiation, the faded echo of the Big Bang itself, is a perfect example. Arno Penzias and Robert Wilson were not looking for the birth of the universe. They were radio astronomers troubleshooting a persistent, annoying hiss in their giant horn antenna, a noise they initially blamed on pigeon droppings. Their pursuit was one of technical cleanliness, not cosmic revelation. Yet by diligently trying to solve a practical problem, they stumbled upon the most important cosmological evidence of the 20th century, a discovery that won them the Nobel Prize. Their happiness, their ultimate satisfaction, came from engaging deeply with a puzzle, not from seeking a predetermined, glorious outcome. This paradox challenges our modern drive for a final theory of everything. In our rush to pin down the universe with a single, elegant equation, we risk devaluing the magnificent, sprawling journey of science. The joy is not just in the destination, but in every unexpected detour, every strange anomaly, every humble admission that the cosmos is far more complex and wonderful than we imagined. Think of watching a meteor shower. If you spend the entire night frantic, camera in hand, obsessed with capturing the perfect shot, you will likely end the experience with nothing but frustration and a few blurry photos. But if you lie back on a blanket, let your eyes adjust to the dark, and simply absorb the silent, fleeting streaks of light across the sky, you are filled with a sense of awe that lingers for a lifetime. The meteors are the same, but your mode of engagement transforms the experience from a failed hunt into a moment of pure connection. So, is the ultimate truth of the universe found only through relentless analysis and dissection? Or does it also reveal itself through appreciative contemplation? The paradox of hedonism suggests that our deepest cosmic insights may arrive not when we are striving most fiercely, but when we are quiet enough and open enough to simply observe the universe as it presents itself, in all its mysterious, unanswerable glory. A perfectly tolerant society faces a slow death from within. If it tolerates the intolerant, those groups will eventually seize power and dismantle the very framework that allowed them to flourish. This is the paradox of tolerance, a philosophical dilemma posed by Karl Popper, and it echoes in the laws that govern our cosmos. Does the universe itself practice a form of tolerance, allowing for every conceivable possibility, or does it impose strict, intolerant limits that make our existence possible? The answer lies in the numbers that define reality itself. Consider the cosmological constant, the value that drives the acceleration of the universe's expansion. If this number were even slightly larger, the universe would have blown itself apart before galaxies could ever form. If it were slightly smaller, gravity would have caused a catastrophic collapse long ago. This precise value is not the only one mathematically possible, but it is one of the very few that allows for a complex, structured cosmos to emerge. This is the fine-tuning problem, and it suggests the universe is profoundly intolerant of most configurations. It has drawn a line in the sand, permitting a narrow range of possibilities that lead to stars, planets, and life, while excluding an infinity of sterile or chaotic alternatives. This cosmic intolerance is enforced by fundamental laws like the second law of thermodynamics, which dictates the relentless increase of entropy or disorder. This law gives time its arrow, preventing the universe from slipping back into reversible, timeless chaos. It is a rule that limits what can happen, ensuring that eggs scramble but never unscramble, and that stars burn fuel in one direction only, from order to disorder. This directional constraint is what makes history and life itself possible. We see this selective process at work in the hearts of stars. For a star to forge the heavy elements essential for planets and life, conditions must be exquisitely precise. The force of gravity must be strong enough to compress the core to immense temperatures, but the nuclear forces must be tuned to allow for fusion without causing the star to detonate instantly. The universe does not tolerate all possible nuclear reactions, only a specific set that, over billions of years, can cook hydrogen into carbon, oxygen, and iron. Philosophers and cosmologists like Lee Smolin have pondered whether these laws are absolute or if they themselves evolve. In a vast multiverse, perhaps countless universes are born with different physical constants. Most of these universes would be stillborn or barren, instantly collapsing or expanding into meaningless vapor. Only the rare, intolerant universes, the ones with laws that strictly forbid certain destructive outcomes and permit stable structures, would ever produce beings capable of wondering about their origins. In this cosmic landscape, our universe is not a free-for-all. It is a carefully curated gallery where the laws themselves act as a selective filter. So, does the universe favor certain structures? The evidence screams yes. From the spiral arms of galaxies to the double helix of DNA, the cosmos exhibits a preference for patterns that can persist, complexity that can endure, within the rigid boundaries it has set. This paradox reveals that true cosmic diversity is not born from infinite permissiveness, but from a delicate balance of freedom and constraint, a set of rules that, by saying no to almost everything, makes something like us possible at all. Freedom can feel like a prison when the options are endless. A supermarket aisle with 200 kinds of cereal does not liberate you, it paralyzes you. This is the paradox of choice, and its shadow stretches from the grocery store all the way to the edge of the observable universe. We now know our galaxy contains billions of planets, and our telescopes reveal billions of galaxies, each a potential island of mysteries. In the face of such cosmic abundance, how do we even begin to choose what to study? This is not an abstract problem. It is a daily reality for astronomers who must point the most powerful instruments in history at a microscopic sliver of the sky, knowing they are ignoring countless other wonders. The psychologist Barry Schwartz identified this modern ailment, where an overabundance of options leads not to satisfaction, but to anxiety, regret, and ultimately, a paralysis that prevents any decision at all. His work reveals that after a certain point, more choice does not increase our freedom, it diminishes our happiness. This principle applies with terrifying force to cosmology. Consider the flood of data from missions like the Kepler Space Telescope. It did not find a handful of new worlds. It uncovered thousands of candidate exoplanets, a vast celestial catalog of possibilities. Scientists could not investigate them all. They were forced to develop triage, to create filters for habitability, to focus on a precious few Earth-like candidates orbiting within the Goldilocks zone of their stars. The very act of choosing what to observe fundamentally shapes our knowledge of the cosmos. We are not mapping the universe as it is. We are mapping the tiny fraction of the universe we have decided is worth looking at. This creates a subtle but powerful observer effect on a grand scale. Our picture of reality is sculpted by our priorities, our technological limitations, and even our cultural biases about what is important. This leads to a tyranny of small decisions in science funding. A committee chooses to fund one telescope design over another. A review panel favors one research proposal. Each choice seems rational and incremental, but over decades, these small decisions can steer entire fields of science, creating massive blind spots. We might pour resources into hunting for dark matter while overlooking a simpler, more elegant explanation, simply because it fell outside the chosen path. How do we find meaning in a cosmos of endless alternatives? The answer this paradox suggests is counterintuitive. True discovery requires not an open field, but a focused beam of attention. Limitation is not the enemy of science, it is its essential partner. Without constraints, without having to choose, we would be lost in a sea of stars, adrift in a universe of pure potential but devoid of any understanding. The cosmic challenge is not to see everything, but to choose wisely what to see, and in that deliberate act of focused curiosity, to find a truth profound enough to make the infinite manageable. A legal contract can trap you in a perfect circle of logic. In ancient Greece, the sophist Protagoras agreed to teach Euthyphus law with a peculiar condition. Euthyphus would pay his tuition only after he won his first case. After his education, however, Euthyphus avoided the courtroom, leaving the bill unpaid. An exasperated Protagoras sued his own student, presenting a dizzying argument to the court. "If I win this case," Protagoras declared, "the court will force you to pay me. But if I lose, that means you will have won your first case, and by our original contract, you must pay me then. So you pay me whether you win or lose." Euthyphus, having learned his lessons well, offered a mirror image of the same logic. "If I win," he countered, "the court says I do not have to pay. But if I lose, then I will have lost my first case, and by our contract, I still do not owe you anything. So I never pay you at all." This is the paradox of the court, a perfect logical loop where the argument consumes itself, and there is no clear way out. We are in a similar bind when we try to understand the cosmos, because we are using the universe to study itself. Our telescopes and our theories are not outside observers looking in. They are products of the very laws they are trying to decipher. We are like a character in a novel trying to use the story's own plot to understand the author. The instruments we build to measure quantum particles are made of atoms that obey quantum rules. The light we use to see distant galaxies is itself governed by the cosmic laws we are attempting to prove. This creates a profound risk of circular reasoning, where we assume a principle in order to prove it. The cosmological principle is a perfect example of this tricky footing. This cornerstone of modern cosmology states that on large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. But how can we possibly know what the universe looks like from a point a billion light-years away? We have never been there. We assume it is true because it seems to hold from our limited vantage point, and it makes our equations work. We are generalizing from a single data point, our own, to the entirety of existence. This is the problem of induction, where we draw a universal conclusion from a finite set of local observations. Every swan we have ever seen is white, so we conclude all swans are white, until we travel to Australia and see a black one. In cosmology, we have only one universe to observe, and we are stuck inside it. We use the light from distant stars to understand the expansion of the universe. But our understanding of that light relies on the laws of electromagnetism, which are part of the universe we are testing. It is a closed loop. Quantum mechanics makes this self-reference even more intimate. The observer is not a passive spectator, but an active participant embedded in the system. The act of measurement, as we have seen, forces a definite reality into being. So when we probe the cosmos, we are not reading from a pre-written script. We are collaborating in its creation. Our consciousness, our technology, and our location are all part of the experimental setup. Can we ever achieve a truly objective, God's eye view of reality from within it? Or are we forever trapped in a hall of mirrors, seeing only reflections of our own assumptions and methods? This paradox does not mean that science is futile. It means that our knowledge is always contextual, always framed by our perspective. Our viewpoint is both the most powerful tool we have and the ultimate trap. the lens that lets us see and the glass that contains us. Even an all-powerful God confronts a simple, devastating question. Can it create a stone so heavy that it cannot lift it? If it can, then its power to create is unmatched, but its strength is limited. If it cannot, then its creative power has a boundary. Either way, its omnipotence shatters against this logical rock. This theological riddle, the paradox of the stone, is not just a puzzle about divine power. It is a profound mirror for the cosmos itself. We must ask, does the universe, in all its vastness, have absolute, unbreakable limits? The answer seems to be a resounding yes, written into the very fabric of physical law. The speed of light in a vacuum is not a suggestion. It is a universal speed limit, a cosmic traffic law that nothing with mass can ever break. Time and space themselves become warped and meaningless for anything trying to accelerate beyond that ultimate velocity. On the opposite end of the scale, the Planck length represents a different kind of boundary, a smallest possible unit of distance. Beyond this point, our concepts of space and time simply break down, dissolving into a quantum foam where the words here and now lose all meaning. These are not limitations of our current technology. They are fundamental features of the stage upon which reality plays out. The universe operates within a rigid framework of logical consistency. Stephen Hawking and others have grappled with the idea of a theory of everything, a single set of equations that would describe all forces and particles. But would such a theory be truly self-contained, explaining its own existence and rules? Or would it inevitably point to something outside itself, a deeper reality or a set of meta-laws that govern even the laws of physics? This search for ultimate explanation often leads to an infinite regress, a hall of mirrors where every answer requires another, more fundamental question. This is where the multiverse hypothesis offers a strange kind of resolution. In an infinite ensemble of universes, each with its own unique set of physical constants and laws, the concept of what is possible explodes. In one bubble universe, gravity might be 1 billion times stronger, and in another, the speed of light might be only 10 miles per hour. Yet within each of these cosmic domains, the rules are still fixed and absolute. A being in a universe with a different speed of light would still be utterly bound by that new limit. Their omnipotence would be just as constrained as ours, just by a different set of numbers. The most dramatic example of a cosmic limit may be the Big Bang singularity itself. Our current physics describes it as a point of infinite density and temperature, a state where all known laws of physics cease to function. It is not that the laws are broken there, it is that they no longer apply. The singularity represents the ultimate edge of what we can describe, a boundary beyond which our understanding cannot pass. It is the universe's own version of the unliftable stone, a condition so extreme that the cosmos's own power to create and sustain breaks down. So, are there absolute limits to what the universe can do? The evidence suggests that reality is not an endless field of pure possibility, but a carefully structured domain of what is logically and physically consistent. The universe cannot create a married bachelor, a square circle, or a logical contradiction. Its power is immense, but it is a power that operates within a framework of rules, a cosmic constitution that even the cosmos itself must obey. This paradox forces us to abandon childish fantasies of limitless power and instead marvel at the elegant, structured potency of a universe that can weave galaxies and consciousness from a set of unbreakable, and perhaps even beautiful, constraints. Our very existence in a life-friendly cosmos might be the very clue that confirms an infinite number of dead ones. We return to the ravens, but this time the cage is the entire multiverse. Observing that our own universe is perfectly tuned for life is like finding a single winning lottery ticket in your hand. It is astronomically unlikely, but if there are an infinite number of players in an infinite multiverse, then someone, somewhere, must hold the winning numbers. We are simply that someone. This applies the same twisted logic of Hempel's paradox to the grandest scale imaginable. Finding our own fine-tuned universe, this one non-black, non-raven, indirectly supports the existence of a vast ensemble of other universes, even though we can never see them. Philosopher Nick Bostrom frames this with a stark choice. Either we are incredibly lucky to be in the one and only universe that works, or our universe is one of many, and we naturally find ourselves in one of the rare, habitable ones. The latter just seems more statistically plausible. This is anthropic reasoning in its most powerful form, where our own consciousness becomes a piece of evidence in a cosmic trial. But is this truly science, or is it untestable speculation dressed up in mathematics? The debate rages among physicists like Max Tegmark, who champion the multiverse, and skeptics who see it as a philosophical surrender. The core of the issue lies in the measure problem. In an infinite multiverse, how do you count the universes? How do you assign a probability to any particular kind? If an infinite number of universes are lifeless wastelands, and an infinite number are lush gardens, then both infinities are perplexingly the same size. Saying life-permitting universes are rare becomes mathematically meaningless without a way to compare these infinities. This is not just a technicality, it is a crisis for making any predictions at all. Bayesian reasoning offers a way through this fog. This approach updates the probability of a hypothesis as new evidence arrives. Before you knew you existed, the chance of a multiverse might have seemed low. But the moment you account for your own existence as an observer, the probability shifts dramatically. Your life is the new data that tilts the scales. This logic folds back on itself in the simulation argument. If even one advanced civilization ever runs vast numbers of simulated realities, then the number of simulated minds would dwarf those in base reality. Therefore, from your perspective, the odds are high that you are in a simulation. Your own consciousness, again, becomes the evidence for a hidden plurality of worlds. It is a dizzying loop. Does the simple fact that we are here to ask the question prove that other realities must exist? This is the circular but potent engine of modern cosmology. We use our local observations to make grand claims about the global structure of everything, and the most local observation of all is our own sentient existence. The paradox reveals that in our quest to understand the cosmos, we are both the detective and a key piece of the evidence, trapped in a beautiful, self-referential loop where the act of wondering about other worlds might be the very thing that confirms them. We have journeyed through 25 cosmic paradoxes, each one a thread pulled from the tapestry of our conventional reality. From the profound silence that answers the Fermi Paradox to the quantum ghost that haunts the Double-Slit Experiment. From the warped time of the twin paradox to the logical knots of self-creation and self-destruction, these are not isolated curiosities. They are interconnected symptoms of a single, staggering truth. The universe is not a static stage upon which we passively perform. It is a dynamic, participatory mystery, a cosmic dance where the observer and the observed are locked in an intimate embrace, and our very consciousness seems to play a role in the melody of existence. The key takeaway from this entire voyage is that reality is far more fluid, interconnected, and fundamentally mysterious than our everyday experiences suggest. The solid ground beneath our feet, the relentless tick of the clock, the independent reality of the moon and stars, all of it is an illusion born of our limited perspective. Embracing this uncertainty is not a surrender, but an awakening to a grander, more wondrous cosmos. Carl Sagan once reflected that somewhere, something incredible is waiting to be known. These paradoxes are the signposts pointing toward that incredible something. They invite you to look up at the night sky with fresh eyes, to question the very foundations of what you think is real, and to seek your own answers in the vast, dark ocean of the unknown. We want to hear which of these 25 paradoxes resonated most deeply with you. Was it the haunting silence of the Great Filter, the philosophical vertigo of the Boltzmann Brain, or the strange intimacy of the quantum Zeno effect? Share your thoughts in the comments below, and subscribe for more journeys into the heart of space mysteries. Remember, the universe's greatest secret may be that it is designed not for our easy comprehension, but for our endless, wondrous discovery. The ultimate destination of our journey may be a simple admission we do not know. These paradoxes are not walls, but horizons, and the pursuit of them is what propels science forward. Each contradiction, each logical knot, forces us to invent new mathematics, to conceive of new realities, to stretch the human mind to its breaking point. The mystery of dark matter exemplifies this beautifully. We see its gravitational grip on galaxies, we map its cosmic web, yet it remains utterly invisible to our finest instruments. This is not a failure of our models, it is a guidepost, pointing toward physics beyond the standard model, toward discoveries we have not yet dreamed of. The greatest scientists have always understood this humble relationship with the unknown. Isaac Newton, after revolutionizing our understanding of the cosmos, saw himself not as a master, but as a child playing on the seashore, diverting himself with a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before him. This is the awe that lies at the heart of true discovery. It is in this space between the known and the unknowable that art and science merge. Cosmologists must be artists, painting pictures of multiverses with the mathematics of string theory, and composers, listening for the faint vibrations of gravitational waves in the silent symphony of spacetime. They use creativity to envision the geometry of higher dimensions and the birth of universes from nothing. This requires a mind that is both rigorously logical and wildly imaginative, capable of holding two contradictory truths at once without panic. The real failure is not in having unanswerable questions, but in losing the curiosity to ask them. Today's paradox, like the baffling wave-particle duality of a century ago, may become the cornerstone of tomorrow's technology. So what new riddles await us beyond the cosmic horizon? Does consciousness play a deeper role in the architecture of spacetime? Are we alone in a silent universe, or is the silence itself a message we have yet to decode? The true reward is not a final answer, but the perpetual state of wonder, the lifelong engagement with a cosmos that is forever grander, stranger, and more mysterious than we can possibly conceive.